So then I think I'll make a start introducing our speaker of today. It's really my pleasure to welcome Peyman Milanfar. Peyman is a principal scientist at Google Research since 2014, where he leads the computational imaging team. Prior to this, he was a professor of electrical engineering at UC Santa Cruz, where he was Associate Dean for Research at the School of Engineering from 2010 to 2012. From 2012 to 2014, kind of made his way slowly to Google, I guess. He was on leave at Google X, where he helped to develop the imaging pipeline for the Google Glass, which some of you might remember. I first actually, when looking up your biography, Peyman, I remember me seeing Google Glasses live for the first time in Quito at a conference. One of the plenary speakers had them, which was a kind of June 2014. I was quite impressed by it. So Peyman is really well known for several of his contributions in inverse imaging problems. One of the most prominent ones being his seminal works on image super resolution. Most recently, Peyman's team at Google developed the digital zoom pipeline for the Pixel phones, which includes both the multi-frame super resolution, super res zoom pipeline, and the Razer upscaling algorithm. In addition, the night side mode on Pixel 3 uses Peyman's super res zoom technology to merge images, for vivid shots in low light. Peyman received his undergraduate education in electrical engineering and mathematics from the University of California, Berkeley, and his master and PhD degrees in electrical engineering from MIT. He holds 15 patents, several of which are commercially licensed. So I think Peyman is a really good example for doing very foundational, innovative research that really made it to very, very cool technology. Peyman has been a keynote speaker at numerous conferences, including the Picture Coding Symposiums, the SIAM Imaging Sciences Conference, SPI, and the International Conference on Multimedia. Along with his students, he has won several Best Paper Awards from the IEEE Signal Processing Society. He currently is a distinguished lecturer of the IEEE Signal Processing Society and a fellow of the IEEE for contributions to inverse problems and super resolution in imaging. So I really look forward to your talk, Peyman, with the title Denoising as a Building Block, Theory and Applications. And before I hand over to you, just to say to the participants, if you have questions for Peyman, please put them in the chat or the Q&A box. We can unmute you at the end of the talk if you raise your hand, or we read your question from the chat or the Q&A box. So please do engage, and I very much look forward to your talk. Thanks a lot, Peyman. The stage is yours.
Thank you very much for a very kind introduction. It's my pleasure to present this to you, and thanks for inviting me. So as you just mentioned, I'm happy to take questions also in the middle of the presentation if you prefer. The talk is about sort of three pieces. The first part, I'll give kind of an overview of various denoising techniques and a little bit of theory behind them. Then I'll talk a little bit about some practical ways of building fairly sophisticated filters using denoising. And then there's a little bit more theory related things at the end. So let's begin. Okay, so denoising is sort of, you can think of it as the simplest of inverse problems. The idea is very straightforward. You have a clean signal that is buried in additive noise. Let's say it's Gaussian for the time being. And you measure X, and the idea is that you want to design a filter that will take X and produce U as close as possible to X in some appropriate metric. And of all the different things that we've done in image processing, denoising is one of those things that has really delivered impressively in practice. In fact, we can do denoising, just kind of going back and forth here. These are actual results on images. We can do fairly impressive denoising on mobile devices with images as big as 12 megapixels in a few hundred milliseconds with almost state-of-the-art quality. So there's a very rich history of denoising going all the way back to the very beginnings of the field, if you like. And at the very beginning, of course, there were some fairly straightforward methods that we're all familiar with, some heuristics, and then some L2-based regularization with a Wiener filter. Some additional heuristic things were related to things like the bilateral filter were introduced in the 80s. Although the bilateral filter was introduced much later, it had some precedent in the literature before that. Robust statistics, wavelets, of course, in the 90s, PDE-based methods, then the actual bilateral filter, which was kind of a big deal and still is in some respects, introduced in the late 90s. Self-similarity methods, kind of the next evolution of the bilateral filter, things like non-local means and so on and so forth. Patch-based methods, sparsity-based methods, and of course nowadays, neural networks of all kinds of shapes and sizes and stripes that have been introduced. So there's a ton of work here. And so this kind of prompted us, this is from a paper from 2010 with my student, Priyam Chatterjee, where we asked, is denoising dead? You know, there were so many papers at the time and all the various different algorithms had performance that, at least in terms of mean squared error, were very, very close. And the conclusion that we came to was that they weren't quite, the denoising wasn't quite dead yet, was getting close. It's fair to say that, 10 years later, with the introduction of, especially introduction of the neural network models, we've gotten very, very close to what I think will be as good as we're ever going to get in some respects. And so the question that comes up is, what else can we do with denoisers? And it turns out there's a lot that we can do with denoisers besides just denoising. And so let me give you a sense of this before getting into much of the details. The idea here is that we can solve many much more general inverse problems with denoisers. Things like tone enhancement, high dynamic range imaging, deblurring, super resolution, and much, much more. So here's kind of a crazy example. The image on the left-hand side is blurred. And the image on the right-hand side is a deblurred version of the left image. And what we've used in the process here is a median filter. Now, I wouldn't have imagined in my wildest dreams that somehow a median filter would be relevant to deblurring, but it turns out it is, and I'll explain how in what's to come. All right, so let's talk about general denoising filters. So I like to think about denoiser as a map that takes the interval 0 to 1 crossed with itself n times. So you think about the image x as being ordered into a vector, an n-dimensional vector. And an image is, it doesn't have arbitrary values. If you have an 8-bit image, it's in the range 0 to 255. So let's normalize it and let's say it's in the range 0 to 1. So the functions f take this n-dimensional interval crossed with itself into itself, basically. And this class of functions is very special in ways that I'm going to describe shortly. So let's start with the general nonlinear denoisers. So there's various categories of these that I'll describe. One are so-called pseudo-linear denoisers, and these include things like non-local means, KSVD, VM3D, PLL, et cetera, I'll explain why they're called pseudo-linear denoisers. They basically look like linear denoisers, except that what would be otherwise a convolution operation is actually a data-dependent map. There's the Bayesian denoisers and their approximations, things like maximum a posteriori, minimum mean squared error, and so on. And then there's a whole broad category of things, including PDE-based methods and convolutional neural networks, and so on. Of course, this is kind of an arbitrary breaking up of the categories, but it will help me to kind of put things into a proper perspective. Okay, so let's start with the pseudo-linear denoisers, and I want to describe kind of what they are and how they work. So the idea here is that an output pixel in the output image is a weighted combination of a bunch of input pixels. Now, typically, these input pixels that contribute to the output pixel could be in a local region, or it could be from the entire image. That's what would be non-local filters. Well, what I'm interested in is these weights being possibly data dependent. So if the weights are not data dependent, this is simply a linear filter. It's just a convolution, very simple. But if they're data dependent, then you can do much more sophisticated things. And that's what I'm calling pseudo-linear denoisers. For convenience, let's write these things in the form of a matrix vector operator. So take all the input pixels and index them by j here, xj. And then each of the output pixels will be indexed here with I. And so xi is a weighted combination of the xj's. And I can take all the weights that point to a particular pixel I, and I can stack them into a vector like this. And then I can take all of these vectors and stack them into the rows of a matrix. And so as a result, I'll have a matrix W, and my filter will be expressed as f of x equals W times x. And as I said, W is a function of x, so I'm going to write it in this fashion. So this is what I call the pseudo-linear filters. Let's give you an example of what these weights look like. So take this image of a part of the face of a dog, and there's a red pixel here that I've highlighted and a blue pixel. And if I compute the non-local weights, these are measured using the non-local means framework. This is what the weights are going to look like. So each of these images that you see on the left and right-hand side, if I were to take those and stack them into a vector, they would constitute one row of that matrix W that I just described. Okay, so one row here and one row here. Okay, so it turns out that the pseudo-linear filters approximate Bayesian denoisers. I won't get into too much detail about that, but that is one of the really important reasons why they're so effective. They're computationally relatively easy in the sense that they are computed essentially in two stages. One is a nonlinear stage of computing the weights, and then a second stage is just a linear filter. Once you've computed the weights W of x, then you're just applying those weights to the image as W of x times x. So you have the benefit of having a highly nonlinear filter, but you have also the benefit of this kind of two-stage operation. A few properties of W that will kind of recur throughout the talk, and for other filters as well, is with proper normalization, you can think of W of x as symmetric. Naturally, if you think about it as a normalized set of weights, it's not quite symmetric, but it's close. But with proper normalization, we can make it symmetric. The spectral radius is 1. And what that means is that these filters are typically non-expansive. There are some exceptions. If you're not careful with the way you normalize things, they can turn out to be expansive. But for the most part, you can think of them as non-expansive filters. The eigenvalues of the filters typically decay very, very fast. And that's an interesting property that tells you somehow about the redundancy of images. So if you take an image and you construct a value of the matrix W, because there are recurring patches around the image, that gives kind of a low rank property to W, which leads to fast decay of the eigenvalues. From the filter, you can also define a Laplacian. Laplacian is basically the identity minus W. And the Laplacian action on X is essentially the residual of the filter. So X minus W times X. All right, now let's talk about the more standard Bayesian filters that generally tend to be nonlinear. So the maximum a posteriori is you compute the posterior PDF of U given X, and then you look for the peak. And that's the map estimate. The minimum mean squared error is also related to the posterior. It's the expected value of U given X. And so it is in the form of this integral that you see on the right-hand side. So MMSE and MAP, of course, don't coincide. They might coincide if the posterior distribution happens to be perfectly symmetric. Or if the variance of this distribution tends to be very, very small, then they might get close to each other. Okay, so let's talk in more detail about map denoisers. So here's the formulation for a map denoiser. So you have this argmin. This first term essentially captures the fact that the noise that we've included in the measurements is Gaussian. So you get this quadratic data matching term. And then the second term here is the negative of the log of the prior. And that this prior is the P of U. And so if you compute the argmin of this, you get the map estimate. And for those of you who are familiar with the proximal operators, you will recognize this exactly as a proximal operator, specifically when the operator phi is convex. Now, without going into too many details, I will note that the map estimate can in fact be written in a very specific form. It can be written as x minus sigma squared, this is the variance of the noise, times the gradient of phi sigma of x. So let me take a moment to describe what this means. So phi is just the phi that was up here. Phi sigma is a sort of smoothed version of phi in a very specific way, namely what's called the Moreau envelope. And this, again, falls out of the theory of proximal operators and so on. Just to give you a sense of, graphically what this would look like. So suppose, for example, phi is this L1 function here in blue. So if you compute the smoothed version of this using the Moreau envelope, what you get is the red curve, which happens to be the Huber loss. This is the so-called L1, L2 loss. So here near the origin, between -1 and 1, you've got a quadratic. And then past that, you get basically what looks exactly like an L1 function. And then if you compute x minus sigma squared times the gradient of this smoothed phi, you get exactly the soft thresholding operator that we're all familiar with. So that's kind of the path towards the well-understood, well-studied soft thresholding problem. Okay, now the MMSE denoiser framework. So this was the formulation for it. The integral on the right-hand side is typically very, very difficult to compute, but there are some really nice tricks that help us to formulate this in a much more convenient way. In particular, again, without going into too many details here, the thing that's of great interest here is a formula called Tweedy's formula. This has been discovered and rediscovered many, many times. So Tweedy apparently never published this, but he communicated it to Robbins, who wrote a paper and acknowledged Tweedy in 1956. The work was independently discovered. This result was independently discovered by Miyazawa. It was used by Stein, and then Raffan and Simoncelli wrote about it in 2007. Anyway, so the expression is here on the right-hand side. What you see is the MMSE is x plus sigma squared gradient of p divided by p. Now, what's remarkable about this formula on the right-hand side is, well, first of all, we can rewrite it in this convenient fashion. So x plus sigma squared gradient of the log of p. This is just the log of p, gradient of the log of p. And then you can think of the log of p as another smoothed version of sigma. In particular, it is in fact a blurred version of the prior. So here is P of U, and then the P of U has been convolved with a Gaussian. And so essentially the prior has been blurred, and then you've taken the log, negative log of that, and that's phi sigma tilde. And so this is a smooth version of phi. It's not the same sort of smooth version that you saw before for the Moreau envelope. It's a different smooth version. But what's remarkable about this is that the right-hand side actually no longer requires you to have access to U. All you need is basically access to a blurred version of that distribution, which is P of X. And so this makes it possible for us to build empirical estimates of the MMSE denoiser with only access to the data, whose distribution is going to be a blurred version of the original P of U distribution. Okay, so an example of what this looks like is, again, start with the blue curve as L1 loss. The red is going to be the Bayesian posterior. And then if you compute this smooth thresholding, you're going to get the MMSE estimator, which looks a lot like the soft thresholding, but it's smooth. And so here's a comparison between the two. So the map would be the soft thresholding, that's the blue curve, and the MMSE would be the smooth thresholding, which is the curve in red. Okay, so let me summarize what I've said so far. Pseudo-linear denoisers are of the form W of x times x, and I can write this as x minus the Laplacian of x times x. Map estimates can be written as x minus sigma squared gradient of the Moreau smooth loss, and the MMSE can be written as x minus sigma squared gradient of a different blurred phi. And so the bottom line is that the general form of these denoisers is very much the same. They all look like x minus something, and I'll say a little bit more about what that something is. So the denoisers are, you can think of them as a perturbation of identity. So why is it useful to think about it that way? Because let's say if there's no noise, what's supposed to happen is that the denoiser is supposed to pass the signal through and do nothing to it, right? So in the limit where the noise is very, very small, you're supposed to have an identity operator. And as the noise gets bigger than zero, is non-trivial, then you get perturbations of identity. The next interpretation is the shrinkage, like you've seen. And so here what you have is you take x and you subtract something from it. So you're basically taking something away. You can also think of it as a gradient step. And so you can see here x minus some gradient step proportional to the amount of noise. And here's the gradient. So these are all really, really useful interpretations. So we can think about building denoisers with some of these properties in mind as well. So as I said, the general form is going to be x minus some vector field of x, so x minus v of x. And v of x may in fact be defined generally as a gradient of some energy. So you can write v of x equals the gradient of some E, and then you can define that E to be what you like. Some well-behaved energy function or potential function. And then if you do that, then your f of x can be the gradient of 1/2 the norm of x squared minus E. If you just compute this, you're going to get back to this x minus v of x. So f of x is basically the gradient of E bar of x. And you can think of this as E bar as kind of a complement of E of x. And so what this means is that F, thought of as a map from Rn to Rn, or this small subset of Rn to Rn, is you can think of it as a conservative vector field. So you've got the scalar field E bar, and you're taking the gradient of it. So that is going to be a conservative vector field. And again, because this is the gradient of a vector gradient of a scalar field, the Jacobian of F itself is going to be symmetric. It turns out that this is a useful property to have, and you'll see later how I make use of it. Things that I've said here in this slide don't really apply to W of x times x, so that may be a little bit confusing, but please bear with me. I'll explain that a little bit later. Okay, so one more thing worth saying here before I go into the next part of the talk is this formulation of f of x denoisers as x minus the gradient of some energy is very much related to an idea that's become quite popular and has been around in machine learning for quite a long time. And just to give you an intuition, you can rewrite this equation in a different form. So I can just rearrange it and write the gradient of E as x minus f of x. This thing on the right-hand side is just the residual. And so what it means is that the residual is on the right-hand side and the left-hand side. If E of x, if this energy or potential function is really capturing something significant about the nature of natural images, then that gradient is effectively measuring the local geometry. It's measuring the tangent space of this manifold that presumably describes images very well. And so the bottom line is that good denoisers are learning the geometry of the image manifold. And the thing that I would really highlight, and the thing that really makes the connection between denoising and all of these different methods for score matching and learning the distribution of images, is that a good denoiser effectively is a good prior. If you are able to have a denoiser that does a really good job, it means that it has learned something very significant about the nature of images. And that's what I'm going to use in the last part of the talk. But before I do that, let me kind of make a digression to talking about how we use denoisers in a very practical way. And we've used this in a lot of the practical work that we've done in my team. So I want to talk about a natural decomposition of denoisers and how we can go from a simple denoising filter to much more sophisticated processing in a really straightforward way. So what I claim is that denoisers can very easily produce a perfect reconstruction image decomposition. And this is really trivial, but really significant from a practical point of view. So you can think of a denoiser as acting as an operator splitting operation. So it's basically a splitting of identity, right? So you can write x as f of x plus the residual, right? So the action of the denoiser plus the residual trivially will give you x back. Now what I can do is I can repeat this operation. So I can take f of x and apply f to it again. And again, write that as f of x plus the residual of that process plus the original residual from the previous line. And I can just keep going. And what I end up doing is decomposing things into really smooth parts and then increasingly more detailed parts. And of course, this whole thing is going to be reasonable and it's going to make sense only if f of x is non-expansive. Otherwise, this f of x is not going to be stable. Okay, so let me write this in a bit more formal way. So suppose my f of x is a function of some parameters. That could be, if it's a CNN-based denoiser, let's lump all the weights inside alpha. Or it could be that alpha is just some monotonic function of the variance of the noise that you have. In either event, I can write the same equation, just including this parameter alpha. And then I can repeat this operation. And what I have after n steps is a decomposition where x is split into f applied n times on x plus a cumulative sum of the residuals where each residual r sub k is defined as the difference between the application k times and the application k plus 1 times. So what's significant about this is I can turn this very simple operation that I just did into an engine that will allow me to do very sophisticated, complex image processing. How do I do that? So this is the decomposition. So imagine now I want to recompose these pieces on the right-hand side back together, but do it in a sort of more free way. And the way I'm going to do that is put different coefficients in front of each one of these terms. So put a beta k in front of the residual terms and put a beta n in front of this term. And I'm calling this a recomposition. So you can think of G with parameters beta, and of course the alpha are still there. G is a processed version of x. G of x is a processed version of x. And that processing is going to be a function of these coefficients. And it's going to allow me a lot of liberty to produce all kinds of interesting results. And these parameters, both alpha and beta, are going to be control knobs that I can adjust to get a particular effect. How might I do that? So let's say I use Photoshop and I take an image and I process it using some very complicated set of filters and I get an output. Now I have a pair of examples. I have the input and I have an output. And I have xi and xi hat. Or I can use any complex filter that I have and I can produce these pairs of examples. Now I can use this pair of examples and I can learn the parameters alpha and beta that will best map xi to xi hat. And that's just this expression that you see down here. D is just some training error built on the recomposition function G. and the desired outcome xi hat from the examples, and then some regularization applied to alpha and beta. This basic general framework is going to allow me to do many different operators that the denoiser actually wasn't built for. So here's one way to think about it. So let's say I start with this input. If my filters were, just for convenience, I've written them here in terms of linear filters, but of course they don't have to be. So I can apply the operator many times, and then I can compute these differences. I can even put these through nonlinearities, and now you can see how these are going to start looking like neural networks. And then I can blend them together and get an output that looks very different than the input. The reason why this works is because X hat has been split into a very smooth component and increasing levels of detail. And then I can decide to combine these things to get whatever effect I want. Of course, it's not going to span absolutely arbitrary things, but I'm going to be able to realize many things. But remember, the thing that I just started with is just one really good denoising filter. And I built everything else on the basis of that. And that's really convenient. So here's a few examples of the kinds of things you can do. Here's a picture of this old gentleman, and I can do things like, this image is not really noisy. This was actually a professionally taken photo. It's not noisy at all, or not very much. I've applied the filter and simply reduced the wrinkles on the face. I can also apply a different set of coefficients and get a cartoonizing effect. I can apply the filter many times and get different kinds of filters. And if you swap out the base filter from being, let's say, non-local means to something else, you can also change the effect as you wish. So here's another example. This is dynamic range expansion. This is taken through a screen, basically, and the screen was kind of giving some lack of dynamic range, and we fixed it here. Here's another example, dehazing. It's bridge in London, and we can improve the quality a great deal. And so at this point, I want to pause and see if there are any questions before I get into the next part of the talk, regularization by denoising, that is going to use some of the work that I described in the first part. So let me take whatever the next 3-5 minutes, a quick break, and see if there's any questions.
Yeah, I think Peyman, there is, so Manico has his hand raised, so I'll try to. So Manico, you are allowed to talk if you want it.
Oh, hi. Very great. Nice talk. Okay. On the adding back to the details, it kind of reminds me of the adding back of the usually associated with the Bregman divergence and total variation. I just wondering what's the connection between that specific and your general formulation?
Yeah, that's a great point. They're in fact quite related. So the Bregman divergence and many other methods for adding back detail are related to a concept also in statistics called boosting. Its origins are in something else called twising, and this is something that John Tukey had invented. So they are directly related. The ideas of boosting and twising are that you filter an image or a signal, and then you take the residual and you filter the residual, and you add the filtered residual back to the original filtered signal as a kind of adding additional texture. And so what the decomposition that I described is just a very general way of thinking about that. So your observation is exactly right.
Great, thank you very much. There is another question, I think. So Vivek Goyal, you are allowed to speak now.
Hi, Peyman. I just have a quick question, I hope. Could you comment on thinking of F as a denoiser versus just thinking it's some function? Like, what are you getting philosophically? What is it about thinking of it as a denoiser that actually helps you make all your later progress?
Yeah, you're absolutely right. I mean, that's a really good point. Here, in fact, I've written regularization by denoising. That's the title of the paper that we wrote. I don't know when it was, like 4 years ago. We in fact consider calling it regularization by filtering. Really, what I'm interested in is a filter that has a certain set of properties. Now, it so happens that denoisers are a very general and very well-known manifestation of those filters. But really, the point is, you can think of it as smoothing filters. You can think of them, if you want to map them kind of to the linear filtering scenario, they're just low-pass filters. These are nonlinear low-pass filters. And so, for lack of a better word, we're calling these nonlinear low-pass filters denoisers. But you're right in the sense that the definition really should encompass a much more general class of things.
So Peyman, there are quite a few other questions coming up. Are you happy for me to continue a bit, or you want to continue with your talk and take
Why
them
don't
later?
I continue, because I think I'm a little short on time. So let me continue, and then hopefully we'll have some time at the end. And I don't have a meeting immediately after this one, so if people want to stick around, 5 more minutes after the time is over, I'm happy to do that too.
Excellent, thank you.
Okay, all right. So let me continue with the rest of this. So regularization by denoising. So this kind of brings everything together in terms of the properties of denoisers that I described earlier. So let me start with something fairly straightforward that has been around for a fairly long time. So let's say we want to solve an inverse problem. And here's the formulation on the left-hand side. L of x and y is effectively just a loss function that measures the distance between our measurements and let's say the quantity that we're interested in. And then R is just a regularization, and lambda is your regularization coefficient. One way to compute or define this regularization is using the Laplacian. Now, typically you might see the Laplacian L here as just being a linear operator, but I'm interested in the nonlinear version of the Laplacian that I've described to you before. So X transpose L times X, where L is the Laplacian action on X, so L of X, X. Okay, so this is, as I said, this has been around for a long time, and the reason why people have used it is that it captures a lot of really useful information that you want to encode, but it is very inconvenient in the sense that the Laplacian matrix is actually fairly hard to compute because its dimensions are giant. It's also kind of hard to work with because it is a function of x, but we can kind of circumvent that by thinking, if we're going to solve this problem iteratively, we can think about, at every iteration, we can think about fixing L as a function of the previous iterate, and then treating it as a linear operator, and then in the next iteration, updating it, and so on and so forth. But the bottom line is, if we do that, we don't know exactly what energy is being minimized anymore if we fix L and then update it in the next iteration and so on. So what we wanted to do is to formalize this kind of thing and generalize it. And that was the root of regularization by denoising. So here's how we did it. The Laplacian regularization term that I just described to you can be written as X transpose times X minus WX. Okay, that's just X transpose LX. So what we said was, well, W of X times X was just one kind of filter, one kind of denoising filter. Why don't we just make it completely general and just write it as X minus F of X? This is, after all, the right-hand side, this term inside the parentheses is just the residual anyway. So let's just write the arbitrary residual X minus F of X. Now you can see clearly that this right-hand side would be small, or zero exactly, under 3 separate circumstances. Either X is 0 or X is equal to F of X, meaning that X is a fixed point of this denoiser, or X is orthogonal to the residual, which means that kind of, the residual has kind of sucked out all the information already. Now, one of the questions, if I go back to this and I look at this, one of the important questions is I can decide on any regularization that I want, but the question is, I have to, at the end of the day, differentiate that R of X. So how do I do that? And here, in order to be able to analytically compute a derivative for R, we made a few assumptions, which turn out to be a little bit perhaps unrealistic, but they tend to be true in many denoisers, not all. And more importantly, practical experience has shown that almost any denoiser will work in this framework, even if these assumptions are violated. So what are the assumptions? One is, of course, the differentiability of F. The other one is what we call a homogeneity. So, this coefficient 1 plus epsilon for small epsilon, if you multiply x, scale it by that, it just comes out. So if you take the input to the denoiser and scale it by a number a little bit different than 1, then that scaling just comes out. And the next thing we assumed is Jacobian symmetry. Now, you remember from earlier, I talked about how using an energy-based formulation for the denoiser, I could actually design a denoiser that would have this particular form. And this is why I was after that particular property. And then if we want R to be convex, then all that's required is for the filter to be passive. And as I described earlier, these are essentially smoothing. We're assuming they're smoothing contractive operators. Okay, so there's some implications of this. The most important ones are probably these two, 1 and 2. One says that the f of x is basically equal to its own directional derivative in the direction of x. And you might remember there was this formulation that we had earlier, where f of x is w of x times x. So with these assumptions, f of x is actually a more general version of this pseudo-linear denoisers. And the next property is the filter stability. It says that if I take the argument and I perturb it by some h, then I get x just perturbed in this fashion, and the filter coefficients don't really change a whole lot. And we actually know that from practice. This is why things like bilateral filter and non-local means works. We take an image and we compute the weights from the image, and then we apply those weights. And so the way those weights are calculated is less sensitive to the noise than the actual application. And this is basically reflecting that. And so going forward with these properties in place, what we see is that if we just carry through and compute the derivative of this, compute the Jacobian, compute the derivative of R, the gradient of R, with a few simplifications and these properties that I described earlier, the gradient of the regularization term just turns out to be the residual. So this almost looks like a linear. So you can think of the result that we have here is that the function almost behaves like a quadratic, right? So it's sort of like x squared, where you take the derivative of it and you get x. Here is x transpose x minus f of x, and the derivative turns out to be basically the difference or the residual. And so now we can think about this as a real convenient formulation for solving the inverse problems. Now we have easy access to the gradients of the objective. We can make our objective convex. And we can leverage all kinds of powerful optimization algorithms. And it turns out that even if our assumptions are violated, things still work. And this is still an open question, actually. We don't quite understand why that is. And it turns out state-of-the-art denoisers give state-of-the-art performance in other tasks, including deblurring and so on. I'll show you some examples. So let's take one particular numerical approach, maybe not the most convenient, not the most efficient one, but something that's really illustrative of what we can do. If we take the gradient and set it equal to 0, and then just assign kind of indices here, k plus 1, k here, what you see is that the iterate k plus 1 can be written as this expression here on the right-hand side, and we can guarantee that this is going to converge if the operator f is passive. This is a nice formulation in the sense that we can rewrite it in a really convenient way. So if I rewrite it, if you just highlight these terms, what you see is that this first term here is not iteration dependent. So it's basically a fixed bias. H transpose H lambda I inverse H transpose Y. This is kind of your standard regularized pseudo inverse. This second term here, you see that it's lambda times a linear filter, which is just a convolution, times f of x. So this is f, the denoiser acting on x, and then a linear convolution. So effectively, in a block diagram fashion, I can write this as x goes in, f gets applied to it, m gets applied to it, a bias gets added, and that gives me the next iterate. But I can actually rewrite this in a slightly different way as well. Instead of using x, I can use these intermediate variables z. I can call the output of the denoiser z sub k minus 1. And if I were to do that, I can rewrite the block diagram in terms of z and get this formulation. This is very interesting in the sense that it looks very much now like a neural net architecture. What you have is zk has a convolution applied to it, a bias added to it, and then it's put through a nonlinearity. The difference is that in the standard neural net architectures, this nonlinearity is pointwise, something like ReLU and so on, whereas here it is a much more sophisticated, possibly even global nonlinearity. And this is, of course, related to the learned ISTA formulation from 2010 as well. So you can think of this as taking that inverse problem that we posed earlier, taking the fixed point iteration and then unrolling it essentially into a network. And you can, in fact, now take this network and learn the parameters M and B just from input-output data, and get a completely novel structure based on what we described here. So let's give you a few examples. Here's deblurring. So this is the kind of teaser example that I gave you very early on. Here's on the top left is the ground truth. The middle is the blurred image. And then here's the median. Using the median as the denoiser, we got this result. The one on the bottom is a different method, different denoiser, TNRD. And then there's two other solutions here. P3 is a plug and play method where an ADMM solution to the regularized inverse problem, a step in that is replaced basically where there's a proximal operator and a proximal operator is pulled out and a denoiser is inserted. And that's, of course, closely related with some of the things that I described here as well. Okay, so here's another one. This is the solution, and that's where we ended up with. And this is, again, a completely different use case, 3x super resolution. So what are some of the open problems here? There are many. Red works even when the assumptions are violated. We're not entirely sure why. Oftentimes you have a non-symmetric Jacobians. And if you have a non-symmetric Jacobians, Weirhorst and Schnitter, in fact, showed that you cannot define a regularizer whose gradient is x minus f of x. It's just not possible. And some denoisers might violate the symmetric Jacobian property. Some might violate the homogeneity condition. And they gave an alternative interpretation, which again is related to the score matching stuff, which is helpful in illuminating. But again, some of these questions still stand. We don't know what happens when these assumptions are violated. Our suspicion is that the framework that we've set up and the assumptions that we've made are probably too restrictive. We made those assumptions in a way because they helped us to prove things, but perhaps they're sufficient, but they're not necessary. I think that the assumptions are too strong. Okay, there's been some recent progress. This work, essentially all the credit goes to Regev Cohen, who did this work. And in this new framework, he basically described regularization by denoising as a fixed point projection operation, which kind of ties together a lot of nice pieces from the plug and play that I described, which uses the ADMM framework and RED. It gives you much more flexibility in choosing the denoisers. The assumptions that we made there are much more relaxed than the ones that we made in the original RED paper. And it provides global convergence guarantees under somewhat more relaxed conditions. Okay, so just to conclude, and then we'll open it up to questions. As I mentioned, denoisers, hopefully I've managed to convince you, are really fundamental building block for doing all kinds of things. both in terms of really interesting theory, but also in terms of very, very practical image processing questions. And the form of the denoiser is really important. These are stable perturbations of identity. As Vivek pointed out earlier, they don't really have to be thought of as denoisers. They're just kind of general operators that have these nice properties. They're, you know, contractiveness or near contractiveness and so on. The generality is really striking. You can solve many, many problems. I mean, I think of denoisers almost as the Fourier transforms of inverse problems, right? I mean, they're as important to inverse problems as far as I'm concerned as the Fourier transform is to signal processing. And there are many challenges still remain. As I said, there's these challenges specifically with respect to red and why it works in general, but also I think understanding denoisers is fundamentally important because it gives us insight into the nature of images. And this goes back to what I said very early on in the talk, which is that a really good denoiser has learned something really fundamental about the structure of the images on which it works best. And so with that, I will stop here. There's a bunch of papers, and I'm happy to share the slides later. And I'll take questions now. Thank you.
Thank you so much, Peyman, for a really inspiring talk. And if you agree, I can just continue reading some questions to you. Yeah?
Yeah, absolutely.
Okay, so the first question is by Samuli Siltanen, who asks, in addition to talking about denoisers, you mentioned using in your process any complicated filter, for instance, in Photoshop. Could you elaborate a bit what is required for such general filtering, apart from non-expansiveness?
Okay, so yeah, let me clarify my remarks there. What I meant there is that you could use any sophisticated filter or any mechanism like Photoshop or any other thing to generate input-output examples of what you want to accomplish. And then once you have those input-output examples, you can map them and learn the parameters of the structure that I described to effectively approximate that much more complicated operator with the framework that we had. I hope that answers your question.
Yeah, okay, super. And another question, Peyman, from also regarding the first part of your talk, comes from Plamen Stefanov, who asks, you said that the Gaussian noise case has been solved. How?
Well, I mean, the how is really difficult to pinpoint because there have been, you know, tens of thousands of papers written about it. But the bottom line is, if you want to know how, there's a number of papers that have been written now where, like any other statistical inverse problem, you can study the fundamental performance limits of how well a particular problem can be solved. And these include things like the Cramer-Rao bound, and there are many other bounds from the literature that you can look at. So if we apply those bounds to the denoising problem, even as we did in 2010, what we discovered was that there was very little room between the performance of the algorithms at the time and these fundamental performance bounds. And basically, at this point, that gap has been closed. So we're not just sort of making a random claim that the problem has been solved. It's just that, you know, if you set up the bounds and you compare the performance of the algorithms to those bounds, there's really not much room for improvement.
Yeah. Okay. Okay. Super. Thank you. And Vivek, you can actually still talk, I think, if you wanted to ask your question personally.
Sure. So I wanted to ask if there's already a literature that you could point us to or just discuss on exploiting ad hoc denoisers similarly to what you showed, but to not be so connected to Gaussian likelihoods?
Yeah, so I guess what you mean is that so far, what I described was that a lot of the empirical denoisers that have been developed have been sort of hand engineered. You know, you can think of it as sort of carpentry, right? We take the pixels and we say, you know, kind of intuitively, what would be a cool thing that would give us some, I mean, if you go back to the origins of, for example, the bilateral filter, it was developed very intuitively. Only later it was realized and it was shown that these are empirical approximations to the minimum mean squared error and various other forms. So you're right, there are actually, I would say, the vast body of literature in denoising since the very beginning. If you take the totality of that, the largest part of it is actually completely empirical ad hoc, and it doesn't connect to Gaussian likelihoods or any kind of likelihood at all. It was only in retrospect that people went back and looked at those denoisers and said, the reason why this works as well as it does is because it is approximating something else. So for instance, with BM3D, if you look really carefully at the structure of the algorithm and how it's put together, it is an approximation. It's a very, very good approximation to the Wiener filter. And so in terms of L2 error, it's extremely hard to beat BM3D. And the reason why is because it's a really, really good approximation to MMSE. So I hope I've answered your question. So there's a lot that isn't pinned on Gaussian likelihoods.
I guess I don't know what the queue is here for questions, but if I could follow up, I guess I wasn't very clear. I mean, I guess it's no secret that I've done a lot of work just kind of throwing Poisson likelihoods here and there and throwing in more complicated likelihoods than Poisson likelihoods, like compound Poisson likelihoods for different types of inverse problems, and got a lot of advantage from that. And I'm trying to imagine how to take what you've told us and modify it for my own uses. But I feel like I am kind of seeing Gaussian likelihoods in what you've shown through the form of the gradient. Mm-hmm. And maybe I'm seeing things that aren't really there, but that's what I meant by having things be tied to Gaussian likelihoods.
Yeah, I see what you mean. I think this would be, I'd be happy to follow up with you and have a discussion offline. But I think what you're saying is actually interesting in the general sense that everything that I've described here has been kind of tied to Gaussian likelihoods. But you're right. There's probably a way to interpret these things that isn't hinged on Gaussian likelihoods. There is a lot of interesting theory to be done there as well. So let's follow up. I'd love to talk to you more about this and see if we can come up with a problem we can solve together.
Yeah, that'd be great. Thank you.
Sure.
So Peyman, I'm going to read maybe one more question from the chat this time.
Yeah, go ahead, please.
So Ferdia Sherry asks, if we take the true denoiser to be the projection onto the image manifold, mm-hmm. we retain some of the nice properties mentioned by you, like conservative vector fields, but we generally lose non-expansiveness depending on the geometry of the manifold.
Right.
Is this gap between the true denoisers and denoisers modeled as non-expansive operators a problem? And if so, do you have ideas of how it should be dealt with?
Yes, it's a great question, and this is a question we grappled with precisely in this paper, regularization by denoising via fixed point projection. So that was exactly kind of the point here: is how do you define the set onto which you're projecting? And the real issue here is that we don't actually know what the manifold of images is, so we can't really define a projection to it very precisely. And also, if you do define a direct projection, what kind of operator you get. And it turns out that the class of operators that we can work with are demi-contractive operators. And so this would be the paper I would refer you to. Hopefully we'll answer some more of your questions.
Super. Thank you very much, Peyman. Thank you so much for a wonderful talk and for engaging so nicely with the audience. Thank you very much.
My pleasure.
And I suggest we say goodbye to everyone. Thank you, Peyman. And yeah, the recording of the talk will be made available via the YouTube channel.
Great. And thanks again for inviting me. It was fun.
Thank you. Thanks a lot. Have a good day.
Bye.